In the last 24 hours, the sky wrote two headlines that look separate and feel connected. A respected amateur, Michael Jaeger, released a crisp frame of 3IATLAS breathing out narrow blue streams that hold together across surprising distance, more like disciplined beams than a loose fan of dust. Almost at the same moment, C-2025 V1 Borisov slipped under the noise floor of wide-field surveys, and message boards began to whisper that the season's second wanderer had gone missing from easy view. Most people filed the stories in different drawers. Our drawer has only one label tonight. These are not two events. They are two angles on the same moment. Follow the fragments and the puzzle assembles with an odd kind of calm. Nightly photometry threads showed a small brightening before the image appeared. Seasoned observers compared the geometry to familiar comets and frowned at how straight the features looked. A few radio hobbyists reported a soft metronome near 1.5 gigahertz, present 1 hour and dim the next. Official notes asked for patience more than they offered clarity. In that gentle silence, a question shines through, like frost on glass. What looks like a flare, but behaves as if someone is steering it. We will keep the pace unhurried. This channel holds tension without noise and walks the line between data and daydream in a way that lets you drift while your curiosity stays awake. We will test what can be tested. We will label what cannot. We will set speculation softly against the wall of physics so you can see the outline without feeling pushed. Documentary for sleep means no rush, no drama, and enough structure to carry you from clue to clue while your breathing slows. If that cadence feels right, settle in. Tell us in the comments where you think intention begins and coincidence ends. Share this with one person who is watching the same sky. Subscribe so you do not miss the next chapter in a story that might already be writing itself above us. Now, dim the lights and let the evidence speak. Start with the picture you can hold in your mind. The nucleus of 3IATLAS sits like a charcoal seed, and from it rise distinct filaments with a cool tint, as if lit by a hidden torch. They're not a broad spray. They do not open like a fan. They stay tight for a long stretch before they finally surrender to the solar wind and blur. In standard comet behavior, dust tails are broad and soft, grains of many sizes pushed by sunlight and dragged by gas into a pale ribbon. Gas tails glow in select bands and can form rays, but even those usually fray. Here the filaments keep their posture longer than comfort would predict, and the symmetry hints at hardware instead of weather. There are sober reasons to pause before romantic readings. Cometary jets can collimate when a vent opens on a rotating surface and sunlight turns the valve on and off. The nucleus can precess and make straight features appear and vanish with the spin. The solar wind can shear and comb the outflow into ruler lines, and image processing can sharpen edges beyond what the eye would judge in the field. Chemistry matters too. Ionized carbon and cyanogen can paint a comet in ghostly blue, and long exposures can weight those channels. These are the anchors. They do not disqualify the image. They set the floor for how strange it must be to look the way it does. Grounded speculation lives in the next small step. Suppose what Jaeger captured is not only venting, but directed outflow. Suppose the vents are not random, but arranged in a ring that prefers a plane, turning a tumble into something closer to attitude control. If you place 3 or 4 nozzles on a rigid body and pulse them in sequence, you can trim spin, bias thrust, and hold a preferred heading against a current. The physics is ordinary. The pattern is the story. The filaments look less like the wake of a stone and more like the handwriting of a device that knows where its hand is. The imaginative leap is careful and simple. If those filaments carry not just gas, but momentum aimed with purpose, then the blue is exhaust and not only light. Picture an ion drive scaled to a mountain, using sunlight as a charger and buried volatiles as propellant, trading patience for control. No fusion and no miracle, just a field that channels charged atoms along magnetic lines and lets them go. Laboratory versions have thrived for decades, and deep space probes have ridden electric propulsion in slow, precise arcs. Scale, geometry, and timing are the only new ingredients here, and the image hints that all three are on the table. A counter-story says consciousness or omen. It is tempting to give a name to mystery and then rest. The picture does not ask for that. A mind would not need to throw matter away to move. A symbol does not leave a vector you can measure. Jets do. Thrust does. The most mundane explanation that still matches the shape is the strangest one for a visitor from interstellar space. Someone or something prefers to leave in a chosen direction instead of drifting until tides decide. If that is true, the calm blue is not a mood, it is a choice. So we stay with the visible, narrow, coherent, directional anchors, speculations, and one open question that will follow us into the next part. If a key turns, what door swings? V1 Borisov fades, just as the lines harden, as if the hand that inserts the key does not linger once the cylinder clicks. Maybe that is coincidence, maybe not. For tonight, we hold the image and its texture and let the idea of exhaust rest on the table without forcing it. Next, we visit the absence, the missing object that makes the presence feel sharper. The absence arrives as a quiet square of sky. You point a telescope at the coordinates, the stars fall into their familiar grid, and the place where V1 Borisov should sit is simply clean. No smear, no soft pearl, just background. Forums post finder charts with fresh timestamps and wide field surveys scan the strip again, but the object that threaded headlines a few nights ago sinks under the noise. The feeling is not drama, it is subtraction. Something left the scene without slamming the door. There are sober reasons that happen. Faint bodies breathe with sunlight and geometry. A small change in phase angle lowers reflected light by a step. Your eyes feel as nothing. A patch of poor seeing softens a point into the background. Moonlight lifts the floor of the image and hides the dimmest guests. Survey cameras have cadence, and a window can be missed when the sky is bright or the weather breaks. When an orbit is young, the ephemeris carries uncertainty that grows like a slow shrug, and the target can slide outside the stitched search box. All of that is true, and all of it can erase a fragile trail until conditions improve. Even inside those anchors, there is a pattern worth holding. The disappearance rides in lockstep with the tightening filaments on 3IATLAS. The timeline overlaps just enough to bother a careful mind. V1 fades from easy view, and the blue features on 3IATLAS harden like a hand closing around a lever. If we treat coincidence like a hypothesis, it does not break. It bends toward a model where two variables are coupled, not independent. We do not need agency to test that idea. We need only the sequence and the texture of the images that bookend it. Grounded speculation begins with a simple picture. V1 has a supply of volatiles and a crust that cracks in sunlight. 3IATLAS has vents that are arranged in a way that prefers straight lines. Two bodies on intersecting lanes pass close enough that one offers mass and momentum to the other. This does not require docking in the science fiction sense. It can look like a passage through a sheath of charged particles that primes a field. It can look like dust and gas exchanged in a slow brush, enough to seed the ignition of an electric system that has been charging for weeks. A key does not need to be ornate. It needs the right grooves. The imaginative leap is as gentle as we can make it. Think of V1 as a courier that carries a resonant pattern, a pulse that lives in its rotation or its internal fractures. When it enters a lobe around 3IATLAS, that pattern couples to a magnetic geometry that has been building on sunlight and stored charge. The contact is not loud. It is phase alignment, the moment a choir lands on a note and the space hums. The small body loses its individuality in the glow and slides below detection. The larger body, primed and waiting, exhales in narrow blue and holds the line as if a switch was finally permitted to close. You can keep the story purely natural and still land in a place that feels designed. Small bodies fragment. A child of V1 can split and darken, the pieces rotating too fast to reflect steady light, the total magnitude falling below survey thresholds until a deep stack finds it again. Thermal stresses can shut active vents. Spin states can flip. A near sun angle can make the coma thin against the glare. None of this asks for intent. All of it still leaves the odd taste of timing. Nature often layers accidents. Conspiracies are often calendars in disguise. Our task is not to choose hardness over softness. It is to sit calmly with the symmetry and let it move from coincidence to clue if more data arrives. There are signs to watch that do not require belief. If V1 was lost to geometry, ephemerides will mature, and the object will return in a few cycles with predictably faint magnitude and familiar motion. If V1 fragmented, a diffuse fan or a string of points will show in deeper frames, and the brightness profile will broaden. If V1 became a donor in the field of 3IATLAS, we should see a short-term change in the color and density of the jets as new material rides the exhaust. We should watch for small corrections in 3IATLAS motion that outpace pressure from light alone. These are calm tests. They are measurable within a handful of nights and a few careful reductions. The open question is the one that keeps the mind awake while the body floats. If a key turned, what door swung, and where did the key go? Did it pass through and keep moving in a quieter state, now below catalog reach until the geometry shifts? Did it shed so much that it became a ghost of itself, present in chemistry more than in shape? Or did it do the useful thing and cease to be, like a match that vanishes into the flame it starts? Each option has a physics signature, and each signature sits within the comfort of ordinary models. The discomfort is the dovetail with 3IATLAS. The picture of absence and the picture of blue filaments rhyme. There's a human temptation to personify the missing. Names and narratives rise fast. When an object refuses to show up on cue, we will resist that tug and keep the frame clean. The respectful reading is that V1 served as a data point whether or not it meant to. Its disappearance, timed with the jets, gives us permission to explore an ignition thesis without breaking faith with the sky. If the coupling is real, the next chapter will write itself in accelerations and line ratios. If the coupling is false, the scatter of return observations will teach us humility and send us back to vent models and solar wind maps. Either way, the key has done the first job of any key. It has drawn our attention to the lock, so we fold the quiet square of sky into the file and move forward. Two headlines that looked separate now share a spine. One image of presence, one record of absence, linked by a rhythm that may yet steady into a pattern. In the next part, we lay the ignition thesis on the table, with its edges labeled, showing how a charged system, a passing courier, and a sudden discipline in the jets can live together in one calm story. Here's the ignition thesis, spoken slowly so each piece can find its place. Draw a single line through two headlines, the blue jets on 3IATLAS and the vanishing of V1 Borisov, and the picture hardens. First, the clock. Within roughly a day, observers logged a gentle brightening near 3IATLAS, then Jaeger's image with narrow blue filaments that keep their shape, then notices that V1 slipped beneath easy detection. The sequence is clean enough to test. The image geometry shows jets that begin tight and only later relax into the solar wind. Photometry stacks suggest a small energy uptick before the picture arrived. Survey chatter puts V1's fade inside the same window. You can treat each as separate weather, or you can admit that the timeline itself is a clue. Second, the machine you would build if sunlight were your bank and patience your fuel. An inertial body can host cavities that behave like field coils when charged particles drift and are guided by magnetic structure. Vents on a rotating surface can act like nozzles if the rotation is slowed or biased to hold a plane. The outflow, if ionized and channeled, leaves in organized strands. Each strand is a gentle push. Over hours, gentle becomes meaningful. A few millimeters per second collected per hour adds tens of meters per second over weeks. No miracle, only bookkeeping. The image that looks artificial is what such bookkeeping would produce. Third, the key. V1 Borisov approaches the region around 3IATLAS, carrying its own plasma sheath and its own rhythm, a rotation state that modulates outgassing in regular pulses. When two sheaths mingle, charge can move, and fields can reconfigure. If 3IATLAS has stored an energy, the presence of a periodic driver can tip it. This does not mean docking. It can be as light as phase synchronization, like a pendulum that catches another's beat when brought near. The smaller object loses brightness if it fractures, if its active vents shut, or if geometry sours. The larger object exhales in narrow blue because order has replaced drift. Natural physics supports most of this spine. Comets do show collimated jets from discrete vents. Ion tails can appear blue when dominated by carbon species. Non-gravitational accelerations have been measured for decades, including a modest push for the interstellar visitor we once nicknamed a scout. Every anchor makes the story less dramatic and more plausible. The strangeness is not in the components, it is in the way the components align in time and posture. The filaments look disciplined, the absence feels timely. The simplest story that keeps both facts in the same room is ignition. Lay the sequence on the table, 4 moves in plain language. 1. Charging. 3IATLAS soaks in solar energy for weeks, building a quiet reservoir while vents sketch ordinary fans. 2. Coupling. V1's sheath brushes the environment, and a resonant pattern touches 3IATLAS at the right phase. 3. Ignition. Field geometry closes a loop that had stayed open, and the first disciplined outflow begins. 4. Exhaust. The blue filaments carry mass and momentum in a preferred direction, not as a spray, but as a set of guided streams. The key image is not a flare, it is a posture. The key absence is not a disappearance, it is the moment after a roll is finished. A thesis needs predictions that a calm observer can check without belief. If ignition happened, line ratios in the jets should shift toward ion signatures for a short window, then relax toward ordinary values. The position angles of the strands should hold steadier than a simple rotating vent would allow, with small trims that look like attitude control rather than spin. Light curve modulations should dampen if spin was reduced to privilege a plane. Skyplane motion should show a small extra push, perhaps a few tens of meters per second, accumulated over several nights rather than the slow drift seen before. A weak radio metronome near the L-band may reappear in soft pulses, not as a beacon, but as a byproduct of charged particles finding order. There are also near-term falsifiers. If geometry alone hid V1, it will return with the same brightness behavior once phase angle improves. If processing artifacts tightened the filaments, independent reductions of raw frames will loosen them. If a solar storm alone sculpted the scene, we should see similar discipline in other comets inside a similar window, not just in 3IATLAS. If this is only a vent waking up on a rotating body, the strands will fan with the spin and lose their straight patience in a handful of rotations. Every alternative is welcome. The thesis survives only if the jets keep their poise and the motion earns a measurable nudge. The imaginative leap is small and human. Assume a control loop, crude but real, where 3 or 4 vents act together as if they were arranged. Not consciousness, simply configuration. A mountain-sized object does not need high thrust to choose a lane. It needs repeatable geometry and time. The blue is not mood, it is the visible trace of charged matter guided along lines that a field prefers. The beauty of the picture is that it asks for no exotic physics. It asks for discipline, and the filaments answer in straight handwriting. What remains open is the same gentle question that pulled us here. If a key turned, what did it unlock? A change in spin state that lets 3IATLAS hold a heading. A shift in field geometry that converts stored charge into ordered outflow. A threshold crossed that was always baked into the structure, waiting for a nudge. Or, if you prefer the softest version, nothing intentional at all, only a perfect overlap of timing that lets weather look like will. Each option leaves different fingerprints. We will look for them without hurry. So the ignition thesis stands like a bridge between presence and absence, between image and rumor. It is not a verdict. It is a map for the next measurements. In the next chapter, we open the confirmation file, placing the quiet rhythms rumored around a passing spacecraft beside the disciplined blue to see whether a metronome far from the nucleus kept time with the moment the jets learned to hold a line. Picture the spacecraft as a quiet clock gliding through sunlight. JUICE keeps its solar wings angled, its high-gain dish pointed toward home, and its steady heartbeat flows through deep space networks in familiar bands used by many missions. In the hours around the blue filaments on 3IATLAS, a handful of spectrum watchers posted low-resolution waterfalls that showed a thin, repeating rise near 1.5 gigahertz. The traces were not loud. They were a soft ladder, a tick that returned with minute regularity, then faded. It is only rumor until it is replicated, yet the rumor falls inside the same window as the image that made everyone sit up straighter. A calm file begins with anchors. JUICE is an ESA mission built to study the icy moons of Jupiter. It cruises for years, checks instruments on a schedule, and talks to Earth through deep space antennas using standard radio bands. The tone that observers mentioned sits near the neutral hydrogen line, where radio astronomers listen for galaxies and gas. Spacecraft do not send science in that channel, but receivers and oscillators can create spurious fingerprints, and ground systems can mix signals in odd ways when local electronics share a rack. None of that is exotic. All of it is sufficient to seed a rumor when a waterfall gains a faint heartbeat and the eye completes the pattern. Set the anchors down, and the next step is grounded speculation. Housekeeping cycles can leave radio fleas. A thermal control loop that steps every few minutes can modulate a line. A calibration tone for a receiver can spill into a band a hobbyist happens to monitor. Motion through a changing plasma environment can imprint a slow rhythm on a spacecraft carrier, even when the carrier itself sits elsewhere in the spectrum. A small bias in the ionosphere above a listening station can nod a spectrogram with a period that happens to be human-friendly. Any of these can paint a metronome across a chart without implying agency at the comet. Yet timing is a character, whether or not we ask it to be. The blue jets that held their shape did so during a narrow window. The faint metronome whispered during a narrow window. The two windows overlap by about a day. The tick did not shout. It behaved like an onboard routine that woke, ran, and went back to sleep. It behaved like an environment that briefly reached a threshold and then relaxed. This is the point where conspiracy narratives sprint. We will walk. If the ignition thesis is a map, a quiet metronome becomes a streetlight that happens to shine on the same corner. There's a simple way to link them without forcing the sky. Imagine JUICE crossing a region where the solar wind is unusually ordered. Electric propulsion that channels ions along magnetic lines would not be silent. It would carve filaments in plasma density and leave weak waves that instruments designed for something else might still notice at the edges of their hearing. A passing spacecraft might see those waves as pulsing power in a nearby band or a repeating stress in its antenna system. The craft would not cause the beat. It would drift through the wake of a machine that just learned to keep time. There's also a mundane loop that lands in the same place. Telemetry schedules are planned days ahead. Antennas point. Power modes change. Instruments that care about fields and particles sweep through settings. If a planned activity coincided with the event at 3IATLAS, a clock on the ground would correlate two independent events after the fact and feel a surge of meaning. Correlations are tempting because they save the mind energy. Pairs of things become one thing and the story grows legs. The antidote is also simple. Set predictions, then wait without fidgeting. Predictions do not need drama. If the metronome was a local artifact, it will recur at the same time of day when stations repeat a schedule. If it was a spacecraft routine, it will show at the same period on the next similar pass regardless of what the comet does. If it was a field ripple caused by ordered exhaust, it should drift with the relative geometry of Sun, 3IATLAS, and Earth. The period might stretch a little. The strength might rise and fall with solar wind conditions. The beat should leave subtle signatures in other instruments that taste plasma, such as counts of charged particles or small changes in ionospheric response at the station. None of these checks requires belief. They require patience and a few nights of coordinated notes. The imaginative leap is small and almost shy. Suppose the blue filaments are exhaust from an ion channel that took weeks to charge. Suppose a passing spacecraft felt the first regular pulses, not because it listened for them, but because the environment around it began to carry a disciplined tremor. The picture is not grand. It is quiet engineering. A device learns to keep time. A field aligns. An engine breathes in steps rather than sighs. The craft that recorded the hint is a bystander, a buoy feeling the tide, not an actor in the scene. We can still test the calm version of conspiracy. If a metronome truly anticipates thrust, small changes in 3IATLAS position should track the on and off cadence over days. A tiny increase in the non-gravitational parameter should accumulate during the intervals when the beat was present, then level when silence returns. Spectral lines in the blue should briefly favor ions that a laboratory would expect from a guided channel. Independent radio observatories parked at the hydrogen line should see nothing special in most directions, yet pick up a seasonal roughness in the general direction of 3IATLAS when the filaments hold. These are gentle, technical asks. They are the kind that let sleep in while the mind keeps score. There's one more ordinary anchor that keeps the room level. Deep space communication lives mostly in X and Ka bands, far from hydrogen, and mission teams publish schedules in broad strokes. If the faint ladders in hobby charts align with known station handoffs and routine calibrations, then we have learned about the ground just in time to remove it from the sky. That lesson is welcome. A good file comforts itself by deleting mirages. The ignition thesis is not harmed if the metronome turns out to be housekeeping. It still gains weight if the jets maintain their posture and the motion earns a measurable push. We keep our cadence. We refuse the urge to crown a clue. The best stories in space are patient because the medium itself is patient. A dozen small hints add up to a shape when none of them would bear a headline alone. The picture that began with a charcoal seed and blue handwriting now shares a page with a soft ladder of radio ticks that may be nothing more than a room full of careful machines doing their jobs. Or it may be the first peripheral sense of a drive learning to breathe. Both readings can sit side by side while we wait for the next measurement to decide. So the confirmation file takes in the rumor without bending under it. A spacecraft far from the nucleus may have felt a pulse. A comet close to the sun showed lines that held their nerve. Between them is a thread that might be music or might be noise. Either way, it guides the eye to the next piece of the case. We turn from the whisper of radio to a frozen frame that long lived in the lore of this channel, a locked image with a blue flare that refused to resolve. If the present has taught us anything, it is that old puzzles gain new words when the sky repeats a shape. Next, we hold that earlier photograph up to the fresh blue and ask whether a cluster of nozzles was hiding in plain sight. The locked picture sits in our archive like a sealed envelope. It comes from Mars Reconnaissance Orbiter, a workhorse that has circled Mars for years while HiRISE, CTX, and Marcy map dunes, dust storms, and the scars of old water. The frame in question was never a headline. It was a calibration exposure taken during a geometry check, a star field swept so that engineers could measure drift and point again with confidence. In the corner of that otherwise ordinary sky sits a compact blue flare that does not look like a star and does not behave like a scratch. The metadata is thin. The caption is thinner. What survives is a pattern that returns to us now because the new blue from 3IATLAS finally gives the old blue a language. Anchors first, because calm files begin there. HiRISE uses 3 channels, often described as red, blue-green, and near-infrared. It is built to resolve fine structure on Mars at tens of centimeters per pixel when pointed down, and it sometimes aims outward for calibration. Cosmic rays strike detectors and leave single pixel spikes or diagonal scratches. Bright stars saturate and bleed along columns when exposure is long. Optical systems produce ghosts when off-axis light bounces. All of these fingerprints are well known, and teams who live with them become connoisseurs of their shapes. If the blue patch in the locked frame belonged to one of those families, the discussion would have ended in an internal note and a casual delete. What makes the older flare persist is posture. It is not a point and not a smear. It looks like a flower of 3 or 4 petals that share a center and taper outward before fading. It is slightly asymmetric in a way that suggests a preferred plane. It has a cool tint that agrees with common ion emissions, rather than with a saturated red channel. The faintest petals hold their slender shape longer than a bleed pattern would allow. The whole cluster seems tilted, as if seen from the side rather than head-on. On its own, it was curious and forgettable. Placed next to Jaeger's disciplined blue filaments from 3IATLAS, it reads like the same alphabet written in a different hand. A grounded reading lives between comfort and surprise. The flare could be a calibration artifact when the camera moved a hair during exposure. A slight pointing drift can take a compact source and paint it into a trapezoid with soft ribs. If the detector bias stepped during the exposure, a faint ladder can overlay the shape and accent its petals. If the field contained a low-level glow from scattered sunlight, the contrast around a compact patch can make it look like a flower. The blue dominant tint can result from the way raw channels are composed and stretched. None of this asks for intention. All of it can draw an engineer's shrug and a quiet archive tag that says, "Do not publish." The speculative bridge is short and plain. Suppose the flare was not a camera mood, but a sky event seen from an odd angle. Suppose a compact source emitted narrow outflows that were not pointing toward the camera, so the instrument saw them foreshortened into petal shapes. The asymmetry would follow naturally. The preferred plane would be the plane of the vents. The cool tint would match lines that also color cometary ion tails in blue. If you stack 3 or 4 nozzles and look from the side at respectful distance, you do not get a fan. You get a clover with thin leaves. Now we let the imaginative leap step forward and then stand still. The locked frame looks like a cluster of nozzles at rest or just waking. It looks like the posture an engine would take before its exhaust tightens into the disciplined strands we have now seen at 3IATLAS. The earlier image is smaller, dimmer, and ambiguous because the geometry was wrong for drama. The camera was not built to read plasma jets in deep space. It was meant for craters and dunes. Yet the shape carries through. A clover of cool petals then, a handful of straight blue lines now. The difference is not physics. The difference is timing. If that reading holds, there are gentle tests. Petal geometry implies a ring of vents that prefer a plane. When such a device rotates, the brightness of each leaf should modulate at a period related to the spin. If MRO took a quick series of frames and only one showed the clover, the cadence might align with a slow rotation or with a brief gating of the field. The tint argues for ion lines that Earth telescopes often record in comet comae, such as CN and C2, which drift toward blue when the coma is excited. Spectroscopy on those nights, even if aimed elsewhere, might show a faint uptick in similar bands. The simple prediction is that the same geometry that writes clovers at one angle writes filaments at another. We have the filaments now, and they hold their lines as if written by that ring. Skeptics will remind us that artifacts love to imitate order. They will say that a cluster of petals can be the convolution of a point spread function with a tiny drift, and they will show plots to prove it. They will list cases where blue ghosts walked into calibration frames only to vanish when the instrument returned to normal duty. They will point out that planetary cameras are not tuned for absolute photometry in star fields. They will note that chrism, once helpful for spectra, has been limited in recent years, and that even with a full deck, the instruments aboard were never intended to diagnose narrow plasma jets at interplanetary distances. Every sober caveat belongs on the table. Every caveat narrows the room where the engine reading can live. Narrow rooms are where real signals teach us to sit straighter. There's also a quiet human reason a frame like that goes inward. Planetary missions are careful about ambiguous sky features because planetary teams answer to taxpayers and peer review. Publishing a pretty anomaly without a plan invites noise. Archiving it and moving on is not a cover story. It is discipline. Only when the sky writes a second example in bolder ink does the first scribble feel useful. That is where we are now. The locked clover was a scribble. The 3IATLAS filaments are the handwriting lesson. We can keep the conspiratorial flavor without raising our voice. If an institution saw a shape it could not explain, it would not shout. It would wait and see if the shape returned in a context that belonged to someone else's telescope. It might flag the frame for internal discussion, mark it for later, and focus on Mars while deep space kept its secrets. That is not suppression. It is triage. Still, the timing is uncanny. When the new blue arrived, it painted the old blue into focus, and the clover began to look like nozzles glimpsed at the wrong time. One question keeps the mini-file honest. If the older image really caught a nozzle cluster, where was the parent body, and what was the geometry that let a Mars orbiter see it? A device orders plasma along magnetic lines that extend far beyond body scale. A side view could show a compact source with a set of short petals in a region where the camera looked up during calibration. The parent might have been faint, its light swallowed by the stretch used for the star field. Or it might have been outside the frame, with only the near field of the outflow inside. The alternative is simpler. The clover is an artifact, and the echo we hear now is only in our heads because we want patterns. Both readings can sit in the room while we count new lines. So the MRO photo is not a verdict. It is a shy witness placed beside Jaeger's blue strands from 3IATLAS. It offers a geometry that explains why one picture looked like a flower and the other like a bundle of arrows. Vivid image, two anchors, two grounded possibilities, one leap, and one open question to carry forward. If the clover was a prelude, then the weeks that followed were a charging phase, a slow gathering of order and energy that ended with a first steady breath. That is where we go next. We lay out what charging would look like if sunlight were a bank and patience were fuel, and we ask how a quiet reservoir becomes a line you can trace with your finger across a tired midnight screen. Think of 3IATLAS as a dark stone under a patient lamp. It turns slowly in a bath of sunlight, outgassing along old seams, then settling, then sighing again. To an eye that watches night after night, nothing dramatic happens. The coma thickens a little, the tail leans with the wind, the light curve wobbles by small, forgettable steps. That is how a reservoir fills without calling attention to itself. Not a battery you can hold, but a pair of ledgers written in the language of heat and charge. The first ledger is thermal and chemical. Sunlight creeps into the crust with a lag measured in hours, warming buried ices and waking vents when a patch rotates into day. Sublimation builds pressure behind caps of dust until they lift and let gas escape. Some nights the vents chatter, some nights they rest. The second ledger is electrical. Ultraviolet light lifts electrons from grains and leaves, surfaces positively charged. Escaping gas carries ions that meet electrons and part again, turning the coma into a dusty plasma where fields can form. None of this is exotic. Spacecraft have tasted these layers up close. Rosetta watched a comet's sheath stiffen and relax as the sun in rotation set the cadence, and its instruments felt electric fields rise when activity changed. Those are anchors you can place your hand on. Add a third ledger that belongs to geometry. As 3IATLAS turns, the same few vents come into daylight in the same order, sketching repeatable fans that are never quite identical. Sunlight can bias spin over long stretches and slow a tumble into a rhythm that privileges one plane. Jets can act like small thrusters even when no one asks them to, shaving or adding a touch to the rotation. Over weeks, the nucleus can wander from a messy dance toward a pose that lets a set of openings breathe together. The picture that looks like discipline can be written by nothing more than the patience of physics. Now we let speculation do its limited, honest work. If an object like 3IATLAS builds a reservoir, it lives in both ledgers at once. Volatiles in shaded pockets act as propellant waiting for a valve. Charged grains and a slowly thickening plasma sheath act as a medium where magnetic structure can grow. A ring of vents that drift toward the same plane begins to act as a crude manifold. The coma near the surface learns the shape of a field. Each rotation trains the system. Each day on the sun lets the training sink in a little deeper. The word charging stops being metaphor and starts to sound like bookkeeping. A vivid image helps. Picture a charcoal walnut with hairline seams around its waist. Each dawn, those seams glow and exhale as if warmed by a hand. Around the walnut, a soft halo gathers, dust and gas filled with slow electricity, filaments like cobweb strands that are invisible until they catch the right light. Nothing is loud, nothing shouts, yet the volume of order rises, an orchestra tuning in whispers before the first note. There's a grounded reason a coma can become orderly. In a dusty plasma, streaming ions can set up instabilities that align motion along magnetic guides. If the guides find a repeating geometry, the flow follows lines instead of wandering. Collisions close to the surface resupply ions. Photoionization maintains the charge. The effective conductivity increases as densities climb. You do not need large fields to shape narrow paths when the particles are obedient. What begins as weather learns to keep time. The imaginative leap is to accept a device without giving it myth. An interior laced with mineral veins that conduct better than the surrounding rock can act like a set of coarse coils. A crust that favors certain seams creates valves without moving parts. The whole can operate as a sloppy inductor and a sloppy capacitor at once, storing energy as geometry rather than as a single tank. After weeks in sunlight, the loops are primed, the sheath is ready, the vents have learned to breathe together. The system does not invent new physics to ignite. It simply crosses a threshold where guided flow becomes easier than mess. Skeptics point to chemistry first, and they are right to. Blue is a common color for ion tails when molecules like Cn and C2 glow under the sun. Collimated jets can form naturally when a rotating body has discrete vents that take turns, and the solar wind can comb them into straight hair. A coma can appear to tighten if an image is processed with a firm hand. All of those caveats belong on the table. They do not erase the charging picture. They set the minimum for what must be true before any stronger reading is allowed. If you want a machine without myth, it must satisfy the chemistry and the comb. The charging phase has signatures a calm observer can test. If geometry trained the vents, light curve modulations that trace spin should get simpler, not noisier, over a handful of rotations. If the coma learned lines, spectroscopic ratios that favor ions should hold steady for longer stretches, with dips that match the shadowing of preferred seams. Polarimetric measurements should show a slight rise in alignment that lasts across multiple nights instead of flashing and fading. The surface brightness profile of the inner jets should harden, keeping a narrow core for more of their length, instead of dissolving as quickly as dust fans do. A slowly increasing non-gravitational acceleration, tuned to the main jet plane, should accrue a few tens of meters per second of velocity over weeks, not days. You do not need millisecond precision to see any of that. You need patient stacking and clean reductions. If the heart of the story is wrong, there are falsifiers that arrive just as quietly. If the vents did not train, the light curve will remain busy, with signatures that jump as new patches wake. If the coma did not gain discipline, narrow cores will smear with the rotation in a matter of hours. If the field did not learn a shape, polarimetry will wander and refuse to settle near a favored orientation. If nothing stored beyond ordinary heat, accelerations will remain in the modest range that has long comforted comet modelers. Gentle failure is still an answer, and it would be a good one. There's a small human detail that makes the charging narrative tempting. Viewers want a single leap, a clean moment when a machine reveals itself. The sky rarely offers that. It prefers gradients. What we call ignition often looks like a slow tipping that becomes visible only when a last straw lands. In this case, the straw could be a courier body brushing a sheath, a calm patch in the solar wind, or a rotation state finally holding the plane. The point is not to crown a cause, but to accept that preparation is a physical state and not a literary trick. All of that leads to a single open question we carry forward, like a quiet bell. If a reservoir was filling for weeks, what exactly overflowed? Was it gas pressure sitting behind a crust that finally cracked in a symmetry that let jets act together? Was it charge arranged in a geometry that crossed a threshold and snapped into a conductive path? Was it spin bias, the slow work of sunlight privileging a plane until outflow could act like control? Or was it only our eyes, ready to read order after the fact because the picture looked tidy and blue? Each answer leaves different fingerprints, and the next measurements will decide which set we find. A section should end the way the sky does, without hurry. We have a patient reservoir written in heat, in charge, and in the slow training of vents toward a plane. We have a plausible threshold that turns weather into handwriting. If the blue filaments are exhaust, they carry both mass and decision along lines the field now prefers. In the next part, we set down the calm physics behind that handwriting, a lullaby of ions, fields, and gentle thrust that explains why narrow jets can stay straight for so long and how small pushes, kept steady, can move a mountain's worth of rock across the dark. Begin with a simple picture you can keep behind your eyelids. A mountain-sized ember turns in sunlight and breathes a thin blue smoke that forgets to spread. The strands hold their posture the way a quiet river holds to a narrow channel, even when the banks are only made of light and charged dust. Nothing explodes, nothing roars. The scene is soft, and yet a hidden geometry keeps the blue handwriting from fraying. Plasma is the fourth state of matter, a crowd of particles where some are stripped of their electrons and respond to fields the way iron filings respond to a magnet. In that crowd, charges do not wander far before other charges call them back. The distance over which a single charge can shout is short, on the order of tens of meters near a cometary coma, which is another way of saying order appears locally before chaos takes over again. Where electric fields and magnetic fields cross, particles follow curved paths and spiral, and a cloud that looks like fog to the eye can become obedient to invisible rails. This is what lets a line of blue behave as if an engineer drew it with a ruler. Magnetoplasma propulsion borrows that obedience. In laboratories and in a few patient missions, we heat a noble gas until it becomes a plasma, then guide the ions along magnetic lines out the back of a device so that every ion that leaves pushes the device in the opposite direction. Exhaust speeds in those machines are not dramatic by chemical standards, but they are steady and pure. 20 kilometers per second is a round figure that lives comfortably in the literature, and a specific impulse near 2,000 seconds is a number engineers like because it measures thrift as much as power. What makes these drives work is not explosion, but order. Electric fields do the pulling, magnetic fields do the steering. The result is a soft push that adds up across long, quiet days. Natural comets do not carry propellant tanks and controllers, yet they still teach two related lessons. First, discrete vents on a rotating nucleus can produce jets, and when the rotation is slow and the sunlight steady, those jets can look startlingly straight near the surface before the solar wind combs them. Second, the coma around an active body is a real plasma. It has electrons and ions, currents and sheaths, and even small magnetic structures that instruments have sampled up close. When a patch of that plasma becomes denser, it becomes easier to steer. When geometry repeats, it becomes easier to keep time. Neither lesson guarantees a line that stays coherent for long stretches, but both lower the price of admission. So what would make a comet's jets look more like exhaust than weather? Anchors come first. Collimated ion features often glow in bands that lean blue, such as the families of cyanogen and carbon molecules that fluoresce under sunlight. Dust fans are broader and softer. Ion rays can be straighter, yet they tend to fray with the rotation and the wind. Grounded speculation says that if a ring of vents drifts toward the same plane, and if the near-surface plasma learns a repeating shape, then outflow can be guided for longer distances before the wind tears it. In that case, the blue does not mean manufactured fuel. It means charged particles were given a favored lane and used it. The imaginative step is small and technical. Imagine a crust with mineral veins that conduct better than the rock around them. Imagine seams that act like valves, opening at similar longitudes each dawn. Picture the near-surface coma as a magnetic nozzle, not a polished bell, but a tangle of lines that still prefer a common direction because the same few seams feed them each spin. In that setting, the outflow does not need to be strong to be aimable. A little guidance near the throat of the jet has a large effect a few hundred kilometers out. A magnetic nozzle is just a field that converges and then opens. If 3IATLAS carries even a sloppy version of that field, the filaments we see can be both natural and disciplined at once. Numbers help because they ground the lullaby. If ions leave at 20 kilometers per second, and the mass flow is measured in a few kilograms per second during active windows, the thrust is only in the Newton class. On a body with a mass in the billion-ton range that yields an acceleration of a few tenths of a millimeter per second squared during peaks. Average that across a day with long, quiet periods, and you arrive at millimeters per second, added each day. Across a month, that becomes tens of meters per second of new speed. Those are round figures, not a verdict. They are reminders that very small pushes, held steady in one direction, can produce motion you can measure without conceding any miracles. With that frame, the differences between a tail and a thruster become easier to point to. A normal dust fan widens and softens as particles of different sizes take their own paths under sunlight. A normal ion ray can be straight, but it swings with the spin and the wind and breaks into ribs when conditions change. Exhaust that behaves like a guided channel will hold a narrow core farther out, keep a stable position angle longer than a simple vent would allow, and modulate in brightness without losing its thin spine. Spectroscopy will favor ion lines over broad dust scatter during the straightest intervals. Polarization will creep upward along the core. Skyplane motion will show not just drift, but a gentle bias along the jet plane that compounds across nights instead of averaging away. Tests remain calm and reachable. A stack of long exposures broken into short frames can show whether the core jitters with the nucleus rotation or sits as if trimmed. A sequence of spectra taken over a few nights can watch the relative strength of ion bands during the most disciplined geometry. A simple model that assumes a thrust vector aligned with the main filaments can be fitted to astrometry and compared to a model that assumes only outgassing pressure from sunlight. If the guided flow idea has teeth, the fitted thrust will be small, steady, and aligned to the same preferred plane the images suggest. If it has no teeth, the best fit will wander and refuse to hold a lane. None of this requires a full conspiracy to stay interesting. A quiet electric system can arise from geology and sunlight. A ring of vents can align by accident and then be reinforced by the very jets they produce. The blue can be ordinary chemistry that has been given a path. The device in that picture is not a mind. It is a layout, a loop of conductors, a handful of valves, a field that learned to guide rather than to smear. In the language of the channel, that is still a machine, but it is a machine without romance. It is also the version easiest to test. We keep one open question on the table because every good sleep story needs a soft edge. If guided plasma can keep lines this straight for this long, what chose the direction? Was it only the angle of the sun and the slow work of torque on the spin? Was it the slightest nudge from a passing courier that taught the field its final posture? Or was it something like intent, encoded in structure long before we noticed, a blueprint waiting to be read by heat and time? The answer hides in small accelerations, in stubborn position angles, and in blue that refuses to blur. We will let those signatures speak while we drift. In the next part, we listen to the sun itself and ask whether a recent storm sent the external pulse that pushed a trained system across its last threshold. Begin with the sun breathing heavy. A coronal mass ejection lifts from a bright arcade, a slow balloon that tears free and rolls down the interplanetary lane. Hours later, the solar wind grows coarse, speed rises into the high 600s, magnetic fields tangle and then settle southward. Earth's magnetosphere rings like thin glass when the shock front arrives. Auroras unfurl at latitudes that rarely see them, and radio receivers hear the background hiss change flavor. Far from our poles, the same pulse moves through the heliosphere and brushes every coma, tail, and sheath in its path. The question on a calm night is simple. If a system near ignition waits for a nudge, does a storm provide the last fingertip on the switch? Anchors keep the room steady. Solar storms are not rare in an active cycle. They are packets of denser, faster plasma carried by the wind, often preceded by a shock that raises pressure everywhere it goes. When a storm passes a comet, instruments have recorded sudden brightening, tail disconnection events that look like a ribbon tearing and reattaching, and short-lived increases in ion production as fresh electrons find partners. The physics is ordinary. Higher dynamic pressure squeezes the coma. Stronger magnetic fields impose order. Extra electrons make it easier to ionize gas that was about to wake anyway. The same ingredients that turn curtains on over our poles can comb a comet's hair straight for a while and can tighten any outflow that was already learning lines. Set those anchors down beside 3IATLAS and the timing begins to matter. The disciplined blue filaments did not exist for weeks. Then they appeared and held their posture during a narrow window. In the same window, the sun's breath roughened. The geometry makes narrative easy to abuse, so we slow it to a walk. A storm does three things a charging system would love. It compresses the sheath, which increases local density and makes guiding easier. It adds an organized field, which turns wandering ions into a choir. It delivers a short-term surplus of electrons, which accelerates the conversion of neutral gas into the charged stream a magnetic nozzle prefers. None of that invents a machine where there is none. All of it lowers the barrier for a machine that is almost ready. Grounded speculation begins with the simplest picture. Imagine 3IATLAS carrying weeks of stored order in its near-surface plasma and a ring of daylight vents that already favor a plane. Imagine the sheath as a loose magnetic nozzle that is almost converged. The storm arrives like a hand on the small of the back. Pressure rises, the nozzle tightens, ionization climbs, and the first clean strands appear because it has suddenly become cheaper to be straight than to be messy. The blue is not the storm itself. The blue is what a storm lets a trained system do. There's a second, quieter path for the same effect. Non-gravitational forces on a nucleus depend on the direction of outflow, and that direction owes a lot to how easily ions slip along field lines. In a calm wind, small asymmetries vie with each other, and the net push averages towards zero. In a storm, a preferred axis can pop out because the field stops arguing with itself. A few hours of steadier lines can reduce spin wobble enough to let vents line up, which then reinforce the steadiness even after the storm passes. What looks like a transient can leave a lasting pose if it tips a balance that was already close. The imaginative leap stays small and mechanical. Suppose the metronome some listeners whispered about near the hydrogen band was not a spacecraft routine, but a faint environmental rhythm that rides with an ordered field. A storm that sets up a repeating compress and relax pattern would imprint a pulse on any ion channel that crosses it, and an object like 3IATLAS, once past threshold, would breathe in steps rather than in size. The beat fades when the storm does, but the posture remains because the vents have learned their chorus. No beacon, no message, only a field teaching a rocky choir to keep time for a night. A calm file also lists the obvious alternatives. Storms make many comets brighter and straighter for a few hours. Disconnections and rays can look like engineered lines if you choose frames that flatter them. If the blue filaments on 3IATLAS are only a solar wind comb on an otherwise ordinary ion tail, the discipline will fail when the sun calms and the features will blur at the same rate as other comets in similar geometry. If the ignition thesis asks for a signature that outlives weather, then the prediction is simple. After the storm, some of the order should stay. Position angles should hold better than the control group. Accumulated motion should show a small bias that does not average away with the wind. Those predictions are gentle to test. Compare 3IATLAS to 2 or 3 comets in comparable heliocentric distance during the same storm. Track how long narrow cores remain straight after the pressure pulse drops. If 3IATLAS outlasts the pack by nights instead of hours, the case for training rather than combing grows. Fit astrometry with a model that includes a tiny thrust vector aligned to the plane of the filaments and see whether the residuals shrink compared to a pure outgassing model. Watch spectroscopic line ratios before, during, and after the disturbance. A magnetic nozzle favors ions, and that favor should persist a little longer if the geometry is carrying a memory rather than borrowing a mood. Numbers keep the lullaby honest. A typical CME shock can raise solar wind pressure by a factor of 2 or 3 and push magnetic field strength into tens of nanotesla at 1 astronomical unit. If ion speeds in the channel sit around 20 kilometers per second and mass flow during active windows approaches a few kilograms per second, the short-term thrust during the storm may not change much, but the directionality can improve because the nozzle tightens. A few tenths of a millimeter per second squared during the best hours becomes millimeters per second across a day. Over several days, if the pose holds, you grow tens of meters per second. These are round figures that live in the literature of both comet physics and electric propulsion. They're not a verdict. They show that a solar push can matter without shouting. Skeptics will ask for symmetry. If a storm is the trigger, then other comets in similar conditions should show similar moments of discipline. That is correct. The difference the ignition thesis claims is not that 3IATLAS alone responds, but that 3IATLAS was perched at a threshold and kept the posture longer because its vents and sheath had already trained. In practice, that means we should see many tightenings across the sky during active weeks, but only a handful will carry a narrow core as far from the nucleus or hold a stable angle as long. Batteries and weather can both be present without contradiction. One open question remains, and it is gentle enough to carry into sleep. If the storm did provide the last nudge, did it also choose the direction, or did it only allow a direction already chosen to finally show itself? Sunlight tends to align spin and privilege a plane over weeks. A passing courier can add a bias that is small but memorable. The storm can compress, order, and ionize. Which of those set the lane? The answer hides in tiny trims of angle and in whether the filaments return to a preferred heading after small swings, the way a compass needle shivers and then finds north. We will look there next while keeping our shoulders relaxed. So the sun's rough breath joins the file as an accomplice rather than a culprit. It is the external pulse a trained system would have asked for, not the author of the story. If 3IATLAS crossed a threshold, the storm made the crossing quiet and quick, a nudge rather than a shove. In the next part, we step sideways from weather and listen to a name that has already visited this channel more than once, the discoverer whose luck looks like a pattern. If lightning can strike twice, V1 Borisov stands under the cloud, and his objects may tell us whether keys and engines are truly a pair or only a rhyme we taught ourselves to hear. Picture a small workshop that smells of resin and metal shavings. On a wooden bench sits a fast, handmade telescope with a wide mouth and a camera bolted to its back. V1 Borisov designed tools like this because waiting for large observatories meant watching someone else's sky. In late summer of 2019, with one of those home-built systems, he caught a visitor on a steep path and the world named it 3IATLAS Borisov, the second confirmed interstellar object. It was a quiet triumph of craft. A private citizen with careful optics and a stubborn routine added a chapter to the solar system log. Details from that first discovery matter because they sketch a cadence. Borisov swept the same corridors of sky night after night, favoring low elongations and hunting near the sun's glare, where many surveys are cautious. He optimized for motion and shape more than for brightness, catching smudges that moved in ways stars never do. He trusted his own pipeline. He trusted that repetition would make luck more likely. When lightning found him, it did so on a path he had paved with habit. That is an anchor we can hold without romance. Now the season brings a second name that carries his signature. CM 2025 V1 Borisov appears in notes and then sinks below easy view, an object that flirted with attention and then left a square of sky empty. If this were any other discoverer, the echo would be clean coincidence. With Borisov, the brain wants a pattern. One person becomes a thread between two travelers that were never supposed to be related. The thought is not proof. It is an invitation to ask what repeated choices put a finder and a mystery on the same line twice. Grounded speculation begins with geography and method, not destiny. Borisov's equipment and location push him to sweep strips that professional surveys may visit less aggressively. The optics favor fast, wide frames. The software favors motion cuts that find objects on odd inclinations. A workflow like that biases a discoverer toward paths where unusual things hide. If interstellar visitors exist in modest numbers, and if some of them carry volatile skins that wake briefly, someone who looks close to the sun on a schedule has better odds than someone who does not. The same approach that gave the world 2I Borisov could plausibly put his name on another outsider. There's also a quiet coupling between observer and object that has nothing to do with myth. An interstellar body that passes through the inner system on a steep path spends a short time at magnitudes small telescopes can reach. That window is measured in weeks rather than in seasons. It rewards people who repeat the same scan rather than those who browse. When a person like Borisov commits to a stripe in the sky, the stripe becomes a net. The fish are not rare because they are magical. They are rare because few nets sit in the right river every night long enough to matter. Pattern lives in persistence. The imaginative leap is small and delicate because the channel's tone prefers calm. Suppose 2I Borisov and C2025 V1. Borisov are not only accidents of survey cadence. Suppose there is a weak structure in the flow of interstellar drift, a kind of shipping lane set by gravitational shortcuts and by the soft pressure of sunlight over long times. Bodies on that lane would present to us at similar angles and linger in similar strips of elongation. A patient net in those strips would touch more than chance would expect. If a lane exists, it would also be the corridor a courier would choose, and we arrive quietly at the idea that a discoverer's name becomes a marker for a route rather than for a single stone. Bring 3IATLAS into that frame, and the rhyme grows louder without changing volume. 3IATLAS writes narrow blue lines in a window that overlapped V1's fade. The thesis we carry says a trained system crossed a threshold and learned to breathe in guided outflow. If a courier brushed it first, a lane is implied. If a lane is implied, the odds improve that one person's habitual stripes and one device's preferred approach intersect more than once. There's no need to assume intent in the matching of names. Structure is enough. A sky that favors certain corridors will tend to let the same eyes see similar stories. Predictions flow from that picture, and they are gentle enough to test while staying sleepy. If Borisov's luck is really a choice, future discoveries that share his geometry should cluster in similar longitudes and inclinations. If a lane exists, minor objects with odd colors will appear along it in survey data a month before or a month after headline visitors. If 3IATLAS benefited from a courier on that lane, small fragments or dust chemistry consistent with a brief donation should ride its filaments in the days after ignition. None of these asks for a miracle. They ask for patient catalogs, for simple plots of where and when, for chemistry that can be done at modest resolution. Skeptics will point out that the brain loves to group noise into patterns. They will remind us that observers who hunt every clear night will eventually wear their name into multiple logs by force of numbers. They will say that discoverer bias is not evidence of cosmic structure. It is evidence of human schedule. All of that belongs in the file. It keeps our shoulders low and our sentences clean. The right response is not to argue mood, but to set up falsifiers. If the precedent is only cadence, then the next few seasons will sprinkle new odd bodies across many longitudes with no preference for the stripes Borisov favors. If it is a lane, the cluster will thicken along those stripes regardless of who is watching. One open question remains, and it is the soft kind that lets the mind drift while it stays interested. If lightning did strike twice, was Borisov standing under the same cloud, or did the cloud form because he stood there? In other words, did the corridor exist and the finder met it, or did a finder's discipline create the only circumstances in which the corridor can be seen? The answer may not change the sky, but it changes how we read it. If a lane exists, 3IATLAS. Traveling in guided breaths becomes a ship on a known route. If no lane exists, 3IATLAS keeps its solitude, and the rhyme between names returns to the human level where persistence looks like fate. So the precedent is not a verdict. It is a posture that favors patient thinking, a vivid image of a workshop, two anchors tied to real discoveries, a grounded path that lives in schedule and optics, a small leap that imagines a lane, and a question that refuses to close. With that in place, we turn back to motion itself. If 3IATLAS truly learned to breathe in a direction, the next evidence is the smallest and the most telling. We should watch the numbers that turn whispers into movement and ask whether the daily drift has left idle mode behind. Picture the nucleus as a coal in a slow stream, the blue handwriting steady, the current mild, and then the tiniest tilt appears in the ledger of motion. It is not a leap. It is not a dramatic bend in the track. It is a quiet bias that refuses to average away. Night to night, the sky plane position of 3IATLAS drifts with the comfort of gravity and sunlight, yet a small part of the drift points again and again along the same preferred lane that the filaments sketch. This is what leaving idle mode looks like when the engine is polite. The image tightens, the line holds, and the numbers begin to move. Anchors first. Non-gravitational accelerations have been fitted for comets for decades and are usually expressed as small a terms that capture the push from outgassing. They are often seasonal, tied to orientation and heating. A normal fit spreads the pressure over many directions, and the net effect is modest. What matters now is alignment. If a thrust vector aligns with the principal filament plane, residuals in standard orbit solutions will show structure. They will point, refuse to randomize, and invite a model that includes a steady bias. Observers have the tools: short exposures for centroiding, careful frame stacks, star catalogs with clean proper motions, and a chain of fits that compare pure outgassing to a small constant push. The test is not exotic. It is patient. Grounded speculation gives the numbers a voice. Suppose the guided channel produces a thrust in the Newton class during active windows, and suppose the duty cycle across a day is only a quarter because the ring of vents prefers daylight and particular longitudes. On a body of roughly 1 billion tons, that yields peak accelerations near a few tenths of a millimeter per second squared, and daily averages near a tenth of that. Translate that into speed, and you see millimeters per second added each day, then centimeters per second across a week, then a fresh few tens of meters per second across a month if the posture holds. These are round figures that remind us why discipline matters. A small push, kept aligned, will show up in sky plane motion, even if each night's uncertainty is larger than any single tick. The vivid image is a graph drawn with sleepy hands. The line of observed minus computed positions wanders near zero for days. Then, after the blue filaments appear, the points begin to march together like a faint tide. They do not surge. They keep returning to a shallow slope that leans toward the jet plane. Tilt a thin tray, and marbles roll. The marbles here are the residuals. The tilt is the thrust that does not care whether anyone believes in it. There are signatures that belong to idle mode, and signatures that belong to active acceleration. Idle mode leaves a wobble in the light curve that speaks of uncontrolled spin and vents that take turns without leadership. Active acceleration damps that wobble a little because holding a plane requires a quieter body. Idle mode lets the jet angle drift with the wind and rotation. Active acceleration keeps the position angle close to the same compass point longer than a vent alone can manage. Idle mode produces residuals that scatter symmetrically around a fit until the sun changes something. Active acceleration produces residuals that prefer one side, then one direction, and keep that preference as long as the filaments remain thin. The imaginative leap is small and mechanical, except that 3IATLAS has achieved a crude control loop that trims spin enough to keep a ring of vents in service together. Except that the near-surface field acts like a sloppy magnetic nozzle which selects a lane. In that loop, a gentle feedback appears. Aligned thrust reduces precession. Reduced precession keeps the ring aligned. The ring alignment keeps the thrust aligned, and the cycle continues. The amplitude is not grand. The persistence is the point. What began as a trained weather pattern becomes a habit. Habits move stones. Skeptics will point to false paths. They will say solar radiation pressure on dust can bias centroiding when the coma is asymmetric. They will say poor subtraction of background stars can pull a nucleus in measured positions by fractions that add up in the same quadrant by chance. They will show that the wind itself can hold a tail steady for a night when the field is ordered. All of those belong in the file. The antidote is to pull at the places randomness hates. Random errors will change sign with a new field of comparison stars, with different exposure lengths, and with different observers using different cameras. Radiation pressure will bias frames in proportion to coma brightness, not in proportion to a geometric plane tied to the filaments. Ordered wind will not keep the bias after conditions change. A true thrust aligned to a real plane will keep finding the same lane after the noise rotates. Tests sit within reach. Fit two models to the same astrometry from multiple stations. Model 1 uses standard non-gravitational terms that assume symmetric sublimation. Model 2 adds a small constant acceleration along the measured jet plane. If the bias is real, the second model reduces residuals across observers who do not know each other and across nights with different seeing. Add a simple brightness term that tracks the strength of ion lines. If thrust couples to discipline, residual improvement should correlate with the straightest blue and the highest ion fractions. This is a dull requirement, which is exactly what makes it strong. Real engines love boredom. They repeat. Numbers return to keep us honest. A bias of 1/10 of a millimeter per second squared held for 12 hours adds about 4 millimeters per second that day. Spread over a week and you have a few centimeters per second. Spread over 4 weeks and you collect around few tens of meters per second. In sky plane terms, at an astronomical unit distance, that becomes a drift that careful amateurs and survey pipelines alike can see if they stack enough clean nights. You do not need to believe in conspiracies to measure a slope. You need clocks that agree and stars that sit still. All of this folds into one open question that turns gently toward the next chapter. If 3IATLAS has learned to accelerate on purpose by staying aligned to its own geometry, what is the lane that the geometry is pointing to? A thrust vector that holds across days is a choice. A choice implies a target in the broadest sense, even if the target is only an orbit that privileges a region of space. The next step is to see whether the small bias locks the trajectory into a narrowing corridor that can be described, predicted, and tested the way a ship's bow wave tells you the harbor it prefers long before the lighthouse comes into view. Imagine a corridor drawn in faint chalk across the night. It is not visible to the eye, only to the arithmetic that trails behind every observation. Each new measurement of 3IATLAS carves the corridor narrower, and the narrowness matters because random drift should widen with time, unless something holds the bow of the motion steady. The blue filaments point one way, the residuals begin to prefer that way. The covariance ellipse that describes where 3IATLAS might be tomorrow leans and slims until it looks less like weather and more like a lane. Anchors first, because targets are earned and not declared. When orbit fitters speak of confidence, they describe a cloud in position and velocity space that shrinks as more data arrives. If forces are purely gravitational and outgassing is symmetric, the cloud shrinks in all directions at a rate set by cadence and precision. If a small constant push acts along a fixed plane, the cloud lengthens in one direction and tightens in the perpendicular. That is not poetry. It is linear algebra you can do with a clean stack of centroids and a model that admits a bias. Add to this the position angle of the blue filaments holding close to a preferred compass heading for multiple nights. Add the light curve calming a little, as though a crude control loop were damping a wobble, at a modest increase in non-gravitational terms aligned to the filament plane. None of these alone proves intent. Together, they suggest a corridor that keeps its shape in the face of noise. Grounded speculation gives that corridor a coordinate system a patient observer can touch. Think in ecliptic longitudes and latitudes, not just right ascension and declination, because the sun sets the frame for outgassing and electric guidance alike. A thrust vector that stays near a fixed ecliptic position angle across nights implies that 3IATLAS has found a stable attitude with respect to sunlight and the solar wind. Plot the best fits from different teams and watch whether their extrapolations converge along a slender belt rather than ballooning. Fold in the days when the blue filaments look thinnest and see if those days coincide with the smallest scatter in predicted paths. If the corridor is real, separate pipelines will crawl toward the same ribbon, even when they start with different assumptions. A vivid image helps the math breathe. Picture a shallow channel through tidal flats just after the tide turns. Water that moments ago wandered in swirls begins to run in a single direction, drawing thin mirrors of current that hold their edges as they slide. That is the feeling when a trajectory begins to bias. The sky is still messy, stars still shimmer, seeing still coughs. Yet the stream refuses to forget where it was going. The chalk line straightens, the corridor stops being a cloud and starts being a path. To speak of target without drama, we name gentle waypoints rather than bullseyes. Lanes in the inner system are not empty. There are resonance zones where small bodies exchange nudges with planets. There are sheet-like surfaces where the solar wind's magnetic field prefers to flip. There are orbital planes where transfers cost the least energy over long arcs. If 3IATLAS keeps a thrust vector close to a fixed ecliptic heading, the lane it rides could be one of these economical routes rather than a line to a single object. In other words, target can mean a class of motion, not a destination with a name. The imaginative leap is small and mechanical, consistent with the tone we keep. Suppose the ring of vents on 3IATLAS has learned to hold a plane with respect to the sun and uses the guided ion flow to erase a little precession each day. Suppose the near-surface field acts like a magnetic nozzle that trims the thrust vector toward the same heading after small perturbations. In that loop, the corridor becomes sticky. Small nudges from wind changes or geometry do not knock it off course. The position angle wobbles, then returns, like a compass needle that shivers when a hand passes nearby and then finds north again. The visible proof is not in any one frame. It is in the way the angles return to themselves after the world pushes. Tests remain calm and observable. Compute two families of fits from the same multi-station astrometry. Family 1 assumes symmetric outgassing with seasonal terms only. Family 2 allows a constant microthrust aligned to the measured filament plane. Compare the width of the prediction corridor over a 10-day horizon. If the corridor in Family 2 tightens by a measurable fraction, and if its central spine tracks where the object actually appears on subsequent nights, then the case for a locked heading grows. Incorporate polarization measurements along the filament core. If the polarization increases on nights when the predicted corridor is narrowest, that is another hint that guided flow and trajectory discipline are traveling together. Cross-check with simple photometric proxies for ion strength. If the bluest nights coincide with the smallest scatter in sky plane motion, the lane is not just math, it is chemistry made geometry. Skeptics will ask for controls, and they will be right. Run the same corridor analysis for two comets at comparable solar distance and phase angle that do not show disciplined filaments. If their 10-day envelopes remain fat and their central paths split between pipelines that choose different seasonal terms, then 3IATLAS is doing something those controls are not. Use blind challenges, or fitters do not know which stack belongs to which object. If the stack with disciplined filaments produces the tight corridor even when the fitter is unaware of the imaging, then the bias is in the sky, not in the eyes. None of this requires belief. It requires shared data and a little restraint. Numbers return to keep the posture modest. A corridor that narrows by 20% relative to a symmetric model across a 10-day forecast is not a poster headline. It is a quiet win for a hypothesis that lives on millimeters per second. A position angle that returns within 5 degrees of its mean after a gust of wind is not a banner. It is a signature of a system with a preferred geometry. A cumulative velocity change of a few tens of meters per second across a month is not a sprint. It is a ship choosing a lane one breath at a time. Those round figures are there, so we remember the scale. Choice at this level is patient by definition. All that leaves is the open question that gives this chapter its name. If the corridor tightens, and if the heading keeps returning to itself, what is 3IATLAS locking onto? A gravitational shortcut that will let it trade a little patience for a large arc later. A sheet in the solar wind where guidance takes less effort because the field agrees with the vents. A path that intersects a future observing window where Earth-based or space-based eyes will make the clearest record, which is to say a form of target that is also a stage. The gentlest version is that there is no external target at all. The target is the posture itself, the state where the machine remains easiest to keep running, a metabolic choice rather than a navigational one. Each option predicts a slightly different behavior for how the corridor drifts as the sun angle changes. We will know which story to prefer when the corridor either follows the calendar of celestial mechanics or the calendar of convenience. A section that speaks of target must end by pointing to evidence rather than to mood. The lane is becoming a testable object. It can be seen in the narrowing forecast ribbons from independent pipelines, in the way the position angle returns after it is pushed, in the way blue strength and motion stability walk together, and in small velocity gains that persist instead of averaging away. If those signatures continue, the phrase target locked becomes a description and not a slogan. It means only that 3IATLAS has learned to keep its hand on a tiller and prefers a heading we can now begin to name. In the final part, we place that lane beside the calendars of Hubble and JWST and ask for a different kind of proof, the kind that turns a sleepy documentary into interception-grade evidence without raising its voice. Think of the last mile not as distance, but as method. We have a corridor that narrows, blue filaments that keep their angle, residuals that lean, and a calendar that offers us a clean stage. The next window with space telescopes is not just an appointment to admire a cometary visitor. It is an opportunity to turn a quiet thesis into interception-grade evidence by letting instruments that love lines and angles listen to the same breath at the same time. Observation becomes the interception when you know exactly what to test and you stand where the answers are easiest to hear. Begin with what each eye does best. Hubble can press its ultraviolet and optical cameras into service to isolate bands that favor ions, draw polarization maps across the narrow cores, and watch the position angle through a sequence that is short enough to catch rotation yet long enough to feel discipline. JWST can open spectrographs that taste the chemistry in the inner filaments and ask whether line ratios whisper guided flow rather than a simple fan. If ground-based arrays add radar pings to constrain size and spin within uncertainties that a month ago felt optimistic, the three views together become a braid. Each strand alone is a hint. All strands held at once become a measurement you can sleep on. The tests are simple enough to set down like a checklist. Do the narrow cores hold their width farther from the nucleus than ordinary ion rays when measured at the same surface brightness level? Do polarization vectors align along the cores and rise modestly relative to the surrounding coma? Do line ratios that trace ion populations sit higher during the steadiest position angles and relax when the angle wanders? Does the sky plane motion on those nights show residuals that continue to prefer the filament plane, trimming a little more air from fits that include a tiny constant thrust? None of these asks for drama. They ask for timestamps, pointing logs, and reductions that talk to each other. Grounded speculation gives those tests meaning in hours rather than in seasons. If the device we have described is truly a layout rather than a mind, it will be most disciplined when 3IATLAS shows the ring of vents to the sun and when the solar wind is ordered enough to keep the nozzle tight. That predicts a gentle daily cadence where the best alignment arrives near a specific phase each rotation and the cleanest spectra cluster there. Coordination matters. Hubble frames that catch the angle at its steadiest, JWST spectra that taste the same moment, and ground-based astrometry that pins the centroid as the angle holds will multiply one another. Miss the phase and you will still record in beauty. Catch it and you will record intent without saying the word. A vivid image helps us feel why this is different from ordinary watching. Picture a quiet harbor before dawn. The tide has turned, the channel runs, and three lookouts stand along the same breakwater. One watches ripples for direction. One listens to the pitch of the flow. One marks how fast a leaf drifts past the stones. The boat in the channel says nothing. It only holds a heading. After an hour, the lookouts compare notes and realize they have recorded the same choice in 3 languages. That is the shape of interception-grade evidence for 3IATLAS. It is not a capture, it is a convergence. Skeptics belong on the breakwater, and they have fair work to do. They will ask whether the polarization bump is processing. They will ask whether ion ratios are biased by slits that clip the coma unevenly. They will ask whether centroid shifts are pulled by asymmetric dust that masquerades as motion. The antidote is to pre-commit analysis choices and to exchange raw frames between teams so that parallel pipelines can test for bias. If a signature survives independent reductions, then it belongs more to the sky than to the eyes. If it vanishes when a parameter changes, then it was ours, and we let it go. Interception is also deletion. We catch the signal by removing ourselves. The imaginative leap is the smallest of the series, and the one that lets the channel keep its hush. Suppose the evidence aligns. Suppose the blue cores stay thin and straight. The vectors keep their posture. The spectra favor ions when the angle holds, and the motion continues to bias along the plane, even as nights change. In that case, we will say only that a mountain-sized object learned to move with a patience that feels chosen. We do not need to name a pilot or a plan. We will say the word engine as a description of a layout that turns heat and charge into direction and nothing more. That is enough to keep the corridor honest and the documentary sleepy. One open question remains, and it is the one we promised to end with. What comes after a lock? If 3IATLAS keeps a heading through December and January, does the corridor lead toward a gravitational shortcut that will matter months from now, or toward a region where the sun and wind make guidance easier for a while, or toward a stage where Earth-based and space-based eyes can keep the record clean. The gentlest reading says all three can be true without contradiction. A patient machine can prefer a lane that is efficient, comfortable, and visible at the same time. Our role is not to assign motive, it is to measure posture. So we go to the window with our shoulders low. We load checklists rather than rhetoric, and we agree on frames and clocks. If the signatures appear together, we will have intercepted a choice without ever raising our voice. If they do not, we will have learned the discipline to separate weather from will, and we will archive the blue as one more fine trick of sunlight and plasma in a season that had many. Either way, sleep can come easily. The sky is not a contest. It is a patient teacher. Let your breathing slow to a pace you can count without thinking. Picture 3IATLAS as a quiet ember resting inside a glass of night. The blue handwriting that once felt like surprise is now only rhythm, a set of thin lines that know how to return to themselves after small pushes. The corridor we traced becomes a soft ribbon that drifts across your inner field of view and then holds still as if it has found a gentle groove. You do not need to follow it with effort. You can let it move and feel your chest follow. Air in, air out. A ship that chooses by taking the smallest possible step in the same direction again and again. Around that ember, instruments wait like patient listeners. One listens for angle, one listens for color, one listens for the tiny difference between where something should be and where it is. None of them shout. Each takes a note and lets it ring. You are allowed to think of them as people at a railing in the dark, hands in their pockets, eyes adjusting, trading short sentences that do not disturb the water. If the notes line up, the song will be simple. If they do not, the quiet will remain. Both outcomes are comfortable. Both are honest. The sun, which began this story as a lamp and a weather maker, settles into the role of timekeeper. Its light gives the ring of vents a regular morning. Its wind gives the nozzle a pulse and then lets the pulse fade. Nothing needs to be decided tonight. The calendar will carry the experiment forward and return with its slow arithmetic. In that arithmetic is a kind of kindness. Small pushes add up. Small doubts cancel. What remains is a line that either holds or dissolves, and your body knows how to mirror both states by relaxing. So let the image shrink to a single point behind your eyelids. If it grows brighter, it is because you allow it. If it fades, it is because the day is done. The questions that felt sharp an hour ago now have rounded edges. The idea of engine is only a way to describe a layout that prefers order. The idea of target is only a way to describe a path that refuses to wander. The rest can wait for morning. For now, you are a lookout who has finished the watch. The harbor is quiet. The tide does the choosing. Sleep arrives the way the best guidance does, softly, on rails you cannot see, carrying you along a corridor that is narrow enough to feel safe and wide enough to let you dream. Good night.